The binomial theorem. Let us start by considering Pascal's triangle. Each number in the triangle is the sum of the two numbers on the row immediately above it. So, for example, 5 plus 10 is 15, 10 plus 10 is 20, etc. And notice there are ones down both sides, because 0 plus 1 is 1. These would be the same numbers you'd get as the coefficients of terms when multiplying up brackets. So a plus b all to the power 0 is just 1, because anything to the 0 is 1. A plus b to the power of 1 is just itself, so that's 1 a to the 1 plus 1 b to the 1. A plus b squared is a plus b times a plus b, so you get 1a to the 1 plus 2a to the 1 b to the 1 plus 1b squared, and so on down there. And if you look at the coefficients, they're the same as the coefficients or the numbers you get in Pascal's triangle. Note also that as we travel from left to right in any row, each term has one fewer a and one extra b. So in the bottom row, we start with 1a to the 4, where the next term has only 3 a's but a b. The next one after that has 2 a's but 2 b's, etc. This means that if we want to multiply out, say, 5 plus 2x to the power of 4, we don't actually need to multiply 4 pairs of bracketed expressions together one at a time. We can simply use this relationship. So if a plus b to the 4 is as follows, 1a to the 4 plus 4a cubed b to the 1, etc., we can replace the a with a 5 and the b with a 2x. So we get 5 to the power of 4 plus 4 lots of 5 cubed times 2x, etc. And then when we multiply it all out, we get 625 plus 1000x, and so on. And the important thing, do not forget when simplifying, say, 4 times 5 times 2x cubed to cube the 2. In theory, we could write out Pascal's triangle whenever we wanted to expand brackets like this. But if we were expanding, say, a plus b to the power 17, it would take a long time to write out the appropriate line. Fortunately, there's a button on the calculator that allows us to work out these coefficients, and if that fails, there's a formula for each one that we shall meet later on. This button is the NCR button, and to find the coefficients 1, 4, 6, 4, 1, we type in 4C0, 4C1, etc., where n is the index that the brackets have been raised to, a plus b to the power n, and r is the power of b for each term. If a is 1, we can save time using the binomial theorem by missing out all the a bits, since 1 raised to any power is still 1. But don't forget that the first term still has its 1 coefficient though. So 1 minus 3x to the power 4 is 1 plus 4 lots of 1 to the power of something, but we can ignore it, minus 3x to the 1, etc. Also note that b is minus 3x, i.e. the minus sign is part of b, and that as a result the terms in the expansion will alternate between positives and negatives. Example 1. Use the first three terms in the expansion of 2 plus 3x to the power of 6 to find an approximate value for 2.12 to the power of 6. Firstly, we should note that we'll need to use the value of x for which they are the same. 2 plus 3x to the power of 6 is 2.12 to the power of 6. So 2 plus 3x is 2.12, and we can work out that x is 0.04. Next, we find the coefficients for 6, 6c0, 6c1, etc. They're 1, 6, 15, 20, 15, 6, 1, although we only need the first three, 1, 6 and 15. So 2 plus 3x is 64 plus 576x plus 2160x squared. So to get our approximate value for 2.12 to the 6, we substitute in this 0.04 we get, and we get an answer of 90.496. If you type 2.12 to the power 6 on your calculator, you get 90.785, so it's not far away. Example 2. Find the first three non-zero terms in the expansion of 1 plus 10x times 1 minus 2x to the power of 5. So what we need to do is we need to start by expanding 1 minus 2x to the power of 5 using the binomial theorem, and then when we got an answer, we multiply that by 1 plus 10x. In theory, we need the first three terms, but we shall find the first four just in case. So the coefficients are 1, 5, 10, 10, 5, 1, and so that gives us, when I do a bit of working out, 1 minus 10x plus 40x squared minus 80x cubed, and so on. So we multiply that by 1 plus 10x, and we get 1 minus 10x plus 40x squared minus 80x cubed plus 10x minus 100x squared plus 400x cubed plus etc. So the 10x terms, one's minus, one's plus, they cancel out. And we're left with 1 minus 60x squared plus 320x cubed. So note that it was necessary to evaluate the x cubed terms since the x terms cancelled out. And also note that at all stages, any terms in x to the 4 or higher were ignored. If n isn't given, you can't use the NCR button to find the coefficients, fairly obviously. So instead, what you do, we can use the actual formulae which generate them. So NC0 is always 1, and NC1 is always n. NC2 is always n times n minus 1 divided by 2 factorial. And note that, 4 factorial, for example, means 4 times 3 times 2 times 1, which is 24. NC3 is n times n minus 1 times n minus 2 over 3 factorial, and so on. So, example 3. The binomial expansion of 1 plus ax to the power n begins 1 minus 28x plus 336x squared. Find the values of a and n. So we start by just expanding 1 plus ax to the power n, but using these formulae for our coefficients. So the first term is 1, the next one is n times ax, and the next one is half n minus 1 times the square of ax. So comparing our coefficients, na is minus 28, and half n minus 1 a squared is 336. Now these are simultaneous equations, but they look a bit complicated. Solving this equation is quite straightforward if you use some nifty rearranging. So let's focus on this half n minus 1 a squared. If we double both sides, just get the n minus 1 a squared being 672, but then we can regroup our n's and a's. So get rid of the brackets, so we have n squared a squared minus n a squared, and now the clever bit. We write n squared a squared as the square of na, and we write na squared as na times a. So we've got brackets na squared minus brackets na a equals 672. Then we can replace those na's with minus 28. So we've got the square of minus 28 minus minus 28a is 672, which simplifies to give us a is minus 4. And since na was minus 28, that means that n is 7. That'll do. That's quite a lot of stuff we covered there today.